Well, Jim, thank you again. It has been a crazy couple of days, but so we've tested some devices. We went into the lab. We saw a bunch of work that you've done there. It's been pretty, I would say, pretty remarkable to see what you're working with and what you've constructed. And I think one of the things that I understand better, from what you've said and what Curtis has told me, is this technology, you are intentionally keeping it very stable. You're not making a lot of changes rapidly to it. It's incremental advance so that you're able to test scientifically what's going on. Right?
4 or 5 years ago, we were looking at micronewton level thrusts. And then we got the NASA grants and promised to do a couple of orders of magnitude better. And by the end of the phase 2 grant, we had crudely gotten it to those 2 orders of magnitude better, hundreds of micronewtons. And in the time since then, we've managed to push it up into the millinewton range. And now recently with the devices that you'll be showing your viewers, the thrusts that result are up in the Newton range,
okay, so
which means that we've made an improvement of 1 million in the thrusts that you can detect with this system. The remarkable thing about that is that this hasn't been done by putting in 1 million times more power. It's been done by refining the operation of the devices according to what the theory says should be the case, so that the devices vibrate as freely as possible without making everything else vibrate, because that just absorbs energy. So if you have the device vibrating freely, and then you have it set up so that it can extract a small force, or actually a fairly large force, by coupling it to the rest of the system via some soft springs, you can actually see the force that's being generated in it. And that really, quite frankly, surprised even me that we could get up into the Newton range.
Yeah. I mean, and 1 million-fold improvement it's absolutely breathtaking. And then to take that further, I mean, there are more advances that you plan on making over time, right? Mm-hmm. And again, it's that incremental refinement, and that kind of captured my eye when you'd said, we change one thing and test, right? And that way we don't get carried away. Mm-hmm. But even with that, over time, I mean, 1 million-fold increase in thrust, and then you have peak power that I believe you'd said was newtons for watts, which is amazing, right? And that's just a peak in the middle of the duty cycle. But then taking it, I guess, beyond that, I know that you guys have looked at using smaller piezoelectric devices that could even like tenfold that, right? Mm-hmm. So.
Where we are, and it's really in a sense unintentional, is that a laboratory exploratory device turns out to be something that should be convertible if we can figure out how to mount it without screwing up a whole of the vibrations that take place that produce the effect. If we can figure out how to do that, it'll transform it into something that has some commercial viability for in-space propulsion. It's the obvious first application. But producing forces on the order of newtons from a few watts in a device that weighs 150 grams holds out the promise of being able to use this thing for, my colleagues get after me when I say heavy lift, because they think of heavy lift as lifting tons of stuff with a gigantic rocket that produces millions of pounds of thrust for a brief instant, blowing a lot of toxic chemicals into the atmosphere on the way up. But it should be possible to get something that will self-levitate, and that means eventually that you'll be able to build these things and simply turn them on and have them elevate themselves without blowing toxic chemicals into the atmosphere and so on. Yeah, it's promising. What's the most promising aspect of it is that the experimental work that leads to that conclusion is sufficiently straightforward and obvious so that minute effects that you don't account for, that you haven't accounted for, you eliminate the possibility of it interacting with its environment in the sense of residual gas, because these things are little air pumps in the atmosphere, by running it in the vacuum. And if the vacuum's hard enough, you can be sure that that's not the case. And you can eliminate it coupling to things like the Earth's magnetic field by putting strong magnets in the vicinity of the device and showing that it doesn't have any effect on it. You can replicate the device by using a dummy capacitor, which will make it run all of the currents and all the rest of that, and show that that has no effect. It's the vibration of the device. But the pièce de résistance is a so-called null test, where you take a device and you put equal reaction masses on the two ends so that it's symmetrical and it's producing the effect, presumably, but the effects of the two ends cancel each other out. And then what you have is all of the circumstances of the actual operation, with the exception of the asymmetric masses, large mass on one side, not much mass on the other. And that test is passed fairly handily by these devices. There's a small residual effect because everything isn't exactly symmetrical, but the effect goes down by more than an order of magnitude when the null test. So you know that we're looking at the real thing. All of this is made possible, as I say, by improvements to the system that Curtis Horn has been largely responsible for, both the vacuum system and the bearings used in the devices, and other suggestions like suggesting the momentum analysis, technical details in the momentum analysis that make it fairly straightforward. And Michelle has been doing the tracker work and the momentum analysis, detailed analysis of the results. And what you end up with is something that says, yes, this really actually works.
Yeah, I think that's the most amazing thing. I mean, there are so many truly amazing components to what you're doing, right? And in fact, a moment ago, I was just thinking about the way that you test and measure. So you have a fully digital test and measurement system. It all goes to one computer screen. But then the part that impressed me was being able to take all of that and record it as a bundle and save it so that you can replay each test with all of the data and go through it with a fine-tooth comb. So
yeah, yeah, it's like the file names for the saved picoscope material. I put all of the technical details necessary to identify the run into the name of the file, because I'm not good at keeping logbooks, and keeping a logbook and keeping track of the actual video files would be challenging for someone like me.
Well, I think that most scientists struggle to a greater or lesser degree with that, right? And, again, it goes to this idea of approaching it with dedication and rigor as opposed to changing a bunch of things and seeing what happens. And I think, Elon Musk, right, has been described as doing the startup approach, where they'll make a bunch of changes and say, we think this works, right? And there are definitely some advantages to that in terms of rapid prototyping, but then the disadvantage is in an area where you have to really understand what is going on. You're not going to get that because you change too many things and nothing works. And so that I think one of the real beauties of this has been this methodical approach that's still producing amazing results.
It's very lucky. No, the critical physical insight behind this was Einstein's insight that inertia and gravity are essentially the same thing. It's in the equivalence principle in general relativity, but general relativity got written down as a classical mechanical system, and in classical mechanics, inertial forces do not appear explicitly. They're implicit in the equations that you write down. But Newton's third law, of course, is the thing that makes mechanics work. And that's the one that says when you push on something, it pushes back with an equal and opposite force. Okay? And people go to great lengths to point out that it's pushing back on you, not on itself. But the question is, where does it get the force to push back on you? And Einstein's answer was, well, it must be the gravitational field of the rest of the stuff in the universe that does that. And if you take that and you're willing to do some straightforward calculations using well-established procedures, you find that you get transient fluctuations and the rest mass of objects when the circumstances are right. And it's all based on that. So in a sense, you can say it's Einstein's insight that's behind all this.
Yeah.
It's not warp and wormhole type of physics yet, but it's, in the Star Trek analogy, it's the impulse engine step to space drives of much more exotic nature. So.
Well, and so that goes back to your original inspiration for this, and you've been working on this for 40-something years now, right?
Since about 1990.
Yeah.
Yeah.
So, yeah.
Yes, it's been a long time.
Okay, so 30-something years. And you had told me the other day that you've worked with things like the Mach Lorentz thruster and other variations and approaches to this. And
there are other ways of doing it, yes.
Yeah, but from what I understand, this is the simplest and most straightforward.
This is the simplest one. I figured it was back around 2010 that after trying Mach Lorentz thrusters and a variety of other suggestions that people made for ways of going at it and all that, I just sat down and I said, look, if this is going to work, you got to work with the simplest possible system so that there are the least number of competing effects that you have to deal with and possible ways of misstepping and so forth. And I had built devices of this sort 10 years earlier, around the end of the 1990s, 2000, 2001. These types of devices were used. That was when it got refined. It was when Tom Woodward was doing his master's work with me.
Okay.
And I looked at it and I said, those seem to work. They are extremely simple. That's the way we're going to do this. And I stopped paying attention to people who said, oh, why don't you try this, that, or the other thing? And we're there. The devices are, with a couple of design improvements over the earlier devices, they're essentially the same thing. They're a PCT stack clamped between two masses. And the masses are asymmetric and they produce force. But as I say, we're also there because of Curtis and Michelle. Curtis and Michelle hadn't come along and insisted on this, that, and the other thing, and clean the thing up and get everything working right and so on. The project would be dead in the water.
I appreciate you pointing out that you do have an amazing team in place. I've exchanged emails with several of your team members, and then Curtis has been an absolute godsend. I mean, he is so dedicated, and this just consumes so much of his thought in terms of how to take this, and make everything that much better, and so it's exciting to see that.
You should understand that Curtis has an agenda that goes beyond simply making thrusters that work and can be commercialized. His agenda is that he's convinced that there are steps beyond general relativity that need to be taken theoretically, and his interest at this point is probably at least as much, if not more so, on the physics than it is on the technical aspect of building devices that work.
Well, so in terms of the theory, and I don't want to get too deep into this because I know that your work has been so heavily focused on experiment, but I've heard this expression that basically new science doesn't overturn existing science, it just fits it into a larger framework and helps people understand it from a new perspective. And with Mach's principle, it seems like that's exactly what you're doing. You're not really overturning existing science, right? You're just helping people understand some of the nuances behind it.
Looking at the situation, I'd have to say that in a sense that's right, but in a sense it's not right. That there is a fundamental shift in the way in which you think about the world that's involved in all major changes. In the case of special relativity, it was that there's an upper speed limit to things and so on and so forth. Validity of Lorentz transformation. You have to do things in a Lorentz invariant fashion in order for them to be reasonable. And that's something that if you go back and you read the literature from the time that this was being developed, that there was enormous resistance to. There was a fellow who wrote a history of the ethers and electricity, a noted British physicist whose name I'm blocking on, who simply ignored Einstein in his work, and it was written after relativity theory was well established. General relativity geometrization is something that was enormously resisted, if you read the literature at the time. So if you look at the time that we're talking about now, Mach's principle has been around since Einstein identified it back in around 1910, 12, something like that. The notion that inertia and gravity are related to each other was something. Mach's principle has been identified as such since the time that Einstein first thought about it and got into arguments with Levi-Civita and others and so forth. It's something where people who are formally trained in gravitational physics say that it was a handmaiden to the construction of general relativity, but general relativity was the theory that correctly describes gravity, and that's correct. Up until now, one can say that general relativity is the theory of gravitation. But Einstein didn't include Mach's principle in the sense that he intended it. Okay, it's there in the equivalence principle, which says that inertial effects are essentially the same as gravitational effects. They scale and transform in the same way. So they're both so-called fictitious forces in standard GR. But Mach's principle really means something more than that. It means that it is the gravitational action of distant matter in the universe that produces inertial effects. And what we've done, I guess you could say, what I did at the outset is I said, hey, look, here's all this literature, Dennis Sciama's famous paper on the origin of inertia published in the monthly notices of the Royal Astronomical Society in the early 50s and so on. Basically what I did was I said, look, inertial forces are real forces, just as gravitational forces are real forces. even though you can say on the basis of the equivalence and the scaling and the transformation properties that they're in some sense different than other forces, that they share with those other forces reality in the sense that you can't make them go away. You can cover them up by choosing your coordinates correctly and so forth, but you can't make them go away. And then applying some straightforward techniques for construction of field equations, but not the ones that are used to formally develop general relativity, you can end up with these transient source terms. And then the only question is, are they real? Because if they're real, what they indicate is the operation of a gravitational effect on accelerating masses that is decades of orders of magnitude larger than you normally think of as gravitational forces.
Okay.
It takes the mass of the Earth or the mass of the Sun to produce gravitational forces that are large enough to do the usual things we think about. But it doesn't take that to stretch the seatbelt in your car when you apply the brakes
Yeah.
catastrophically. Yes, you can stretch out the seatbelt in your car. And that's a real force. It's not a fictitious force, it's a real force. And it's, as I say, decades of orders of magnitude larger. And that's really what we're taking advantage of here, is that decades of orders of magnitude larger gravitational effect. And then all you have to do is apply it. Say, okay, well, if we do this and that and the other thing, we can make this fluctuate a bit. And then if we push and pull in the right way on the thing while it's fluctuating, we can extract a real force that will accelerate a spacecraft without blowing anything out the tailpipe. The way I think of it is not as propellantless propulsion, but as recycled propellant propulsion, because you're pushing on something when it's heavier and then pulling it back when it's lighter and so on. Basically what it does is it gives you a way to exchange momentum with the gravitational field of the universe. And it works.
It does work. And so I should ask about replication partners, because that was one of the things that you had mentioned to me yesterday or the day before, was your team is working for qualified people to work alongside them, right? As part of a group project for replications.
Replication has some problems. Most people, when they do replications, go in with considerable, what I call observer bias. If they are convinced when they start out that there can't really be anything to this and that it's all just a bunch of vibrational artifacts, they find a way to come to that conclusion.
Yeah.
You know, and that's happened several times to us. So I'm leery of people who want to, quote, replicate what we are doing. We've made up a bunch of devices so that we have several spares that we can loan out and so on. But my view is that none of those go out for replication unless somebody who knows what they're doing goes along with it, so that the replicator cannot fall into observer bias, as has happened to us several times already.
Well, and knowing the equipment too. I think that is so crucial. You know, things like this, you can't just, pick it up and plug it in, right? This is scientific research. This is not a finished commercial product.
Oh, that's not quite so.
Okay.
Hal took took an amplifier and all the vibration isolation equipment and all that, and delivered it to one of our replicators, set it all up, plugged it in, turned it on, it worked.
Oh,
Yes.
that's amazing.
Oh yeah,
Okay.
it was at that level we had done that, and I made sure that Hal went along with the stuff when it was delivered to make sure they didn't mess it up. But as soon as Hal left, they messed it up. They took the vibration isolation equipment out and bolted the thing onto their balance. And since it vibrates a lot, surprise, surprise, it made the balance vibrate.
Yeah.
And they managed to come to the conclusion that there was nothing there. And so, no, I mean, not only does the equipment go to a replicator, but somebody who knows what they're doing not only helps them set it up, but stays around to make sure that they don't bolt it onto the balance directly in effect.
Well, so your latest version is what you're calling big ears, right? And it has kind of extended bearing flanges. And I know that you've been getting more into bearings and the supports and things like that lately.
The big ears test is because Curtis and I have been having a discussion about how to perfect what's going on. My view is that we can identify vibrational artifacts in a clear and unequivocal way with the way we've got it set up now. And so if there are some vibrational artifacts in the data, we can take them out.
Ah, okay.
You know, and that's really basically all you really need. Curtis wants to get rid of the vibrational artifacts entirely so that they simply aren't present in the first place. And in order to do that, he's bought a bunch of bearings that are too big to fit into the hardware that John Woodland, our university machinist, has so laboriously and elegantly created for us. And so we have a particular device, which I call big ears, because the ears that hold the bearings have to be larger. And one of the problems of these devices, and that can easily mislead you, is that the vibration of the device really is critical. And so if you go and change something that affects the vibration of the device, you run the risk of screwing it up. And big ears is a test to see whether or not you can increase the size of the ears significantly to accommodate these larger bearings or not.
Yeah.
And we'll have a better idea of that later this afternoon after we get big ears back on the balance and see how it works.
Well, it's exciting to see all of these changes, you know, and it's that quest for just continuous improvement, you know. And again, I mentioned this a few moments ago, but I think both yourself and Curtis have talked about the piezos can be made smaller, basically 1 millimeter instead of 2 millimeter, and you could potentially get an enormous boost of power, right? And I think the major roadblock, if I understand correctly, the major roadblock is that changes the setup, and you want to be able to capture valid data, right? So it's got to be fairly similar from one test to the next.
What he's talking about in going to 1 millimeter thick piezos as opposed to 2 millimeters, which the classic versions of these are all 2 millimeters, mainly because it's much easier to make a 2 millimeter thick stack than a 1 millimeter thick. We're going to find out how, if the promise of 1 millimeter thick is that you can run it at lower voltages and get the same field intensities in the dielectric material. And that's advantageous if you're trying to make something that's commercializable. It has nothing to do with the physics as such. So the real problem is, can you do this with something other than 19 millimeter diameter discs? And the answer, at least crudely we know, is yes, because there's a device actually sitting in the thing on the table here that uses discs that are 20 millimeters in diameter instead of 19, and it works. Okay, so yes, we know answers like that, some answers like that. But what we're talking about is what are the initial baby steps and what presumably will turn out to be a serious technological investigation to find out what you can get away with and still produce large effects and what you can't.
Yeah.
And that's something that requires resources that are at the moment beyond our command.
That makes
When
sense.
an angel comes along with a lot of money so that we can hire people to do work and pay them for their time and pay manufacturers to produce things to specification and so on, that'll all take place. But that isn't going to happen until the word gets out that yes, you can get Newton level forces out of these devices, and you can show that the force is a genuine force, that it's being produced in the way in which we say.
Well, and technology like this seems like it's ready-made for the space industry, right? For like adjusting satellites, that seems like that would be a great initial start for it.
Mm-hmm. Yeah. The question is, will it catch on?
Yeah.
And the answer is, I don't know. I assume that it will eventually. Somebody will come along and say, look at it and say, hey, that really does work. And yes, you can't exclude competing explanations in the way in which they say you can and so forth. And there will be progress, but the progress is probably going to depend upon somebody saying, hey, if that really works, it's a significantly cheaper way of doing something that's very expensive to do now. You know, that is to say, it costs less.
Yeah, it costs less, and I mean, again, when you're talking about orbital adjustments in satellites, from what I understand, there are already field effect devices. Like I've read about superconducting magnetic system that's used to change the orientation of satellites in orbit by interacting with the Earth's magnetic field. Mm-hmm. But there aren't any field effect propulsion devices, and so in a strange way, you know, the similar technologies in some ways are already in use, right? It's, you know, propellantless propulsion, but it's not, you can't actually propel things with it. Now, your device, you can actually use that to change orbital altitudes.
Oh, yes. Oh, yeah.
Like that.
No, you can change the orbit with these things in principle.
Yeah.
And one often hears that that's the ultimate test of one of these devices, these type of devices. Can you put it in the satellite and change the orbit?
Well, and these are, I mean, they do vibrate, right? But this is not like those, you know, like the stick shift, you know, I'm thinking of the wrong word there, but, you know.
Stick slip.
Stick slip, yes. You know, a lot of those are the goal is to make it vibrate more in one direction than the other, and those are insane. And so what you have actually is compatible with satellites or larger versions who are compatible with aircraft and things like that.
Stick slip is zero momentum, so you can't change the orbit with stick slip.
Yeah, yeah.
No. You may be able to make a satellite rotate or something like that by using, but it's counter-rotation. It's not simply rotating the whole satellite, because stick slip operates by something pushing off of something else. So this goes this way, the other part goes the other way with equal and opposite momentum.
Yeah, yeah.
No, this is something that will produce a technology that will actually be useful and probably turn out to save people an awful lot of money. You know, it's something that runs off of energy, only it doesn't require that you blow stuff out of tailpipes. So, you know, it's something that will continue to operate as long as you've got an energy input. And in the satellite business, that's simply a matter of solar panels.
Yeah.
And some electronics converted into useful.
Well, what do you see the progression for this being over the next few years?
Over the next few years, I don't know. Maybe this will help. Maybe somebody out there will see the videos that you create and all that, see the results presented, you know, so that at identifying stick-slip events and how you identify them and saying, oh yes, there's something other than stick-slip there. You know? And then the null test will convince them that that's worth at least pursuing to see whether or not we haven't screwed something up. And what they'll find when they do that is, I like to think that we haven't screwed anything up.
Well, I mean, again, the rigor, the quality, the attention to detail, everything that you put into this is so far beyond, you know, the average, I guess. I mean, it's just painstaking work, you know. But the wonderful thing about that is you're able to back up all of this experimental evidence. Not only can you back up the claims, you can show those tests. You have a full screen recording with all the sensor readouts and a video of the thing moving, and it's all there, all in one place. It's all in the hard drive.
Yep. It's instrumented with the stuff that we really need to know. There's one part of the instrumentation which is not essential to this, to get the results that we've gotten, obviously, because we got the results. But what we want to add is some thermal sensing. And Paul March is working on a solution for that, which presumably will be forthcoming sometime soon. We'll add that. But adding that is really the only thing that's missing from this.
Okay.
Other than some much more expensive, much more technically detailed stuff where real resources are required in order to go after it with scanning electron microscopes and things like that. So we've already done a little bit of that sort of work. You know, Hal Fern did that before Hal decided to take a sabbatical from physics a year ago. Hal hopefully will be back, because that.
Yeah, I know Hal was a tremendous force in helping you move this forward. So, yeah, and you know, the impression that I get is that Curtis is taking over at least a little bit of that work, you know, and he is also, I've been so impressed with his assistance on this.
Yeah. Hal was a godsend, no question about it.
Oh, yeah. No, you've had some amazing team members. But I think that comes back to you. You know, this has been, I mean, when people see a project that is based on the right ideas and is being pursued correctly, quality people want to get involved with it, right? And so, you know, you get the kind of people who are willing to take that risk because they see it's being taken responsibly.
Mm-hmm. Yeah.
Let me thank you so much for your time today.
Oh, it's my pleasure, Tim. You know, I'm really delighted that you decided to come down and bring all of your equipment. Yes, yeah, we're looking forward to the next steps. You know,
Okay.
eventually it will work out, I expect.
Thank you again, sir.
Thank you.